Number 8 from the Fall 2012 final has a package sliding down an incline, hits a spring, constant friction force, maximum distance the spring will compress. So the types of problems, especially the ones with springs we worked, always were conservation of energy. So we have initial and a final state. We know energy conservation applies. We just need to account for everything. So let's write out this form: potential energy, kinetic energy, gravitational, potential energy, elastic, plus kinetic energy plus work in is equal to potential energy, elastic final, gravitational final, kinetic energy final, plus losses. So that's how we're going to account for everything. Okay. Let's see. So for gravitational potential energy, we need to set a datum. I'm going to draw the final position of the block right here. Alright, and we'll use the front edge of the block as our reference point. So there's my datum for gravitational potential energy. Okay. It's going to slide down some distance. I'll draw this in green, some distance x right here. That's our unknown distance. Alright, so h is going to be x times the sine of 40. So this relates our change in height for gravitational potential energy to the distance it slid along the block there, along the incline. Okay. So again, we're solving for x in terms of, we're solving for x. Alright, so our elastic potential energy is going to be, initially is going to be 0. The spring is uncompressed. Okay, we will have some gravitational potential energy, so that's going to be, let's write it out in equation terms, mgh. We do have some initial kinetic energy, 1/2 mv squared, and we're not going to have any extra work coming in. Okay, our final potential energy, elastic, is going to be 1/2 kx squared. The distance it slides is the amount the spring is compressed. Our final gravitational potential energy is 0. When it's at its maximum compression point, the velocity is going to be 0. Okay, so no kinetic energy. And energy loss, we do have a friction force here. So that's going to be a force times the distance it slides, which is this x distance we've defined. Okay, so now we can plug in some numbers. 12 kilograms, 9.81. H was x sine 40. Okay, plus 1/2, 12, 5 squared. It's equal to 1/2 K, 900 newtons per meter, x squared, plus our friction force, 42 newtons, times x. Alright, so we have x, and x, quadratic equation. Again, the solver can work this out pretty easily. I'll put everything on the left and use the solver. So clear that out. So 12 times 981 times x sine 40 plus, oops, close parenthesis, plus 0.5 times 12 times 5 squared. Okay. Then those come over, so it's going to be a minus 0.5 times 900 x squared. And that comes over minus 42x. Where'd my 42 go? 42x. Oh, how about 2 meters as a guess? Oops, clear it out to solve. 0.616 sounds reasonable. I worked everything in this problem in terms of kilograms and newtons and meters, so that's why the units will work out to be meters here.